Hi, we're going to look at another type of reaction today, and that's the double replacement reactions. So let's look at the general format of a double replacement. All right, you have cations and anions, and they're paired up with one another in an ionic compound, and they appear to be switching partners. And so here we have the AX and the BY. So the A and the B, these would be your cations or the positive ions. And then the X and the Y would be our anions. And what happens is they switch partners. So now we've got A with Y and B with X. So if you ever see two reactants and they each have a partner, start thinking, this is going to be a double replacement, and they're going to switch partners. Now, what causes them to switch partners? Or in other words, what's the driving force? Well, the reason they like to form products is they want to remove ions from solution. And the way they do that is by forming a precipitate. And a precipitate is something that is not soluble in water. So it's the solid that comes out of solution. Now, how do you know if something is soluble or not? Well, what you need to do is you need to use the solubility rules. And those are in your packet, in your reference chemistry reference tables. So you'll find your solubility rules, and it will tell you what is and is not soluble. And we'll practice with that in class some. So if you, after switching partners, if you form something now that is no longer soluble, in other words, you formed a precipitate, those ions will come out of solution. All right, so again, use those solubility rules. You don't have to have them memorized. They're in your reference table. And if you're doing this in a test tube, like we'll be doing in a lab, the precipitate is going to fall to the bottom of the test tube because it's a solid. And the ions that do not precipitate, so sometimes it'll pair up with something else and it's still soluble. So we call those spectator ions. They didn't do anything. It's like being a spectator at a sporting event or something. You just sit there. You didn't react. You didn't do anything. Okay, so let's go ahead and practice doing this. All right, lead 2 chlorate. Okay, lead 2 has a positive 2 charge, and chlorate is ClO3 with a -1 charge, is mixed with iron 3 bromide. Okay, there we go. Now, I just wrote them as ions because these are solutions. And in solution, in aqueous solution, they exist as ions. All right, now, the lead is going to go with the bromide. Do they form a precipitate? Is lead bromide soluble? And the answer is it is not soluble. It is not soluble. So we're going to put them together, lead bromide, and it's a precipitate or a solid. This S stands for solid. It's a precipitate. I used to, when I was in chemistry, I used to put an arrow going down. That meant a precipitate. But the correct way to do it is to write an S like that. And then, let's see, iron 3 chlorate, is that soluble? And you look on your solubility chart, and all chlorates are soluble. And, well, it is soluble. And so, guess what? The iron 3 and the chlorate are spectators. We just get rid of them. They're not part of our reaction at all. They just are just floating in the test tube. They don't react. All right, now for the balanced equation, it gets really easy. All we have to write are the things that actually reacted. So our lead reacted with the bromide, giving us our precipitate or the solid lead 2 bromide. All right, oh, not balanced. Put a 2 out front here, and now we're balanced. All right, that's as easy as it is. All right, so we just have to look and see what is balanced. This equation that I wrote right here is called a net ionic equation. And a net ionic equation is one where we have just completely removed all the spectator ions. All right, now let's try another one. Ammonium carbonate. Okay, ammonium carbonate. Again, that's soluble. Our reactants will be soluble. And zinc acetate. So I like to envision all these ions floating around in a test tube, and then the ammonium bumps into the acetate. Does it form a precipitate? No, all ammoniums are soluble. The zinc bumps into the carbonate. Does that form a precipitate? And it does. Most carbonates are not soluble. Now, group 1A carbonates and ammonium carbonate are soluble. Just about all the other carbonates are not. And so we are going to write down the precipitate zinc carbonate, and that's our solid. And then notice that the ammonium and the acetate, they didn't precipitate, so we're going to keep them as ions. So there they are. Ammonium, ammonium, and now we can write our net ionic equation. And here it is. Zinc, woo, I'm writing my product first. Zinc plus carbonate yields our precipitate zinc carbonate. And it's balanced. Isn't that nice? Getting rid of those spectator ions just makes our life easier. All right, sodium hydroxide. All right, again, this is soluble, a solution of sodium hydroxide. So we're going to write it as ions, is mixed with magnesium sulfate. Remember, you have that polyatomic ion chart to help you out? All right, now they're all floating in the test tube, and sodium bumps into sulfate. Does it form a precipitate? Nope. Sodium, everything is soluble. So they're still floating around as ions, and as you have guessed it, they are going to be crossed out because they're going to be spectators. Now, what about when the magnesium bumps into the hydroxide? Does that precipitate? And in this case, magnesium hydroxide indeed does precipitate. Most hydroxides are let's see, hydroxides are soluble, except for barium. Most hydroxides are insoluble except for barium, strontium, and calcium. So magnesium hydroxide would be insoluble. So there we go. And there's our solid. All right, and our net ionic would be magnesium, plus we're going to need 2 hydroxides, giving us our precipitate, magnesium hydroxide, solid. Okay, we took our spectators out, and that's our net ionic equation. We're going to be mixing solutions in the lab and writing some net ionic equations and practicing with our solubility rules. All right, we'll see you then. Bye.